stick near the microphone. You'll see that the title on the slide is different from the very long title that's in the proceedings. Seth asked me to do this talk and said, could I give a survey of the long list of things that you see in the title, and then said, oh, and by the way, you've got 20 minutes. So this is necessarily going to be rather selective and occasionally rather superficial. So I'm going to talk about deep learning for natural language processing. And I guess most of you are familiar with neural networks, traditional neural networks, which have been around for 25 or 30 years now and are a kind of standard tool in the machine learning repertoire. And the simplest form of network typically consists of 3 layers. You have an input layer where you feed in the values of a vector of features representing the properties either of the training data item that you're training on or the new bit that you're trying to classify. Each of those input units is connected to all of the units in the hidden layer, and on each of those connections there'll be some kind of weight, and the same between the hidden and the output layer. And the idea is that you feed once the network is trained, you put your input in, do all the multiplications of the weights through the various layers, and then look and see which of the output units gets the highest value, and that's the answer to your classification problem. There are some complexities. To make this a general purpose learning device, you need to apply what's called a non-linearity to the output of the units. This is just something that squishes the value into a small range between 0 and 1 or -1 and +1. And the output layer, because by the time the weights have been trained, you're going to get all sorts of values. They're not going to look like a probability distribution, but you can make them look like a probability distribution by using what's called a softmax function. And the training is via a very neat algorithm called backpropagation. The idea is you've got a training item, you feed it in, you see what your current set of weights gives you for the answer. You look at the difference between your answer and the correct answer, the error, and you propagate that error back through the network to adjust the weights and nudge them in the direction where next time they're going to give you the right value. So the deep learning is basically lots more of the same kind of thing. It's not a completely novel technique, it's just more of the same kind of thing. The difference is that with traditional neural networks, although in principle you can have as many layers as you like between the input layer and the output layer, in practice people always used to find that you didn't get any better performance. They take an awfully long time to train, and the reason for that is because as the errors in the training process, as the errors are going back through the network, they're getting smaller and smaller because they're averaged over all the units. And after a few layers, effectively, there's not much change in the weights. The other problem that people often complain about is that in order to get best performance out of these networks, you need to choose the input set of features very carefully. And there's no algorithm for doing that. It's just trial and error and experience. But it makes a lot of difference. So a good set of features will give you good results, and a bad set will not. So deep learning sells itself as a way of solving most of these problems. So there are several different aspects to what's become known as deep learning, and they're all kind of largely promises at this point, but one is so-called pre-training, the idea that you can crawl over a very large amount of unlabeled data in various ways, and I'll give an example of it, and that eventually that crawling over it will discover useful kind of regularities in the data that later traditional learning stages can capitalize on. So it's a way of discovering features, if you like. The other innovation is that people figured out ways of training layers separately so that the disappearing gradient problem went away. That kind of varies actually in how widely applicable it is. You need often some kind of quite severe restrictions on the type of network you have. And intuitively, the idea is that the different layers would then do what they were originally supposed to do, which was to correspond to different layers of abstraction, that you'd learn kind of low-level features sort of pixel distributions and so on. And then the next level would be things like edges and lines and corners and angles, and then later on things that were more recognizable, intuitive features of whatever you were trying to do. There's a suspicion in the community that actually what the real thing that's made all this possible is that computers have just got cheaper and faster. And since most of what you're doing in neural network stuff is matrix vector operations and graphical processing units are built to do that kind of thing very quickly, you can get an awful lot of speed up. And parallelizing these things, although some aspects of these algorithms are not so easy to parallelize. Okay, I'll give an example. I mean, there are other kinds of things that get called deep learning as well, like things called autoencoders and so on, but I obviously don't have time to cover it. I'm going to give you an example of one kind of semi-supervised pre-training method that's quite commonly used over the last couple of years in natural language processing. And this is something called word embeddings. And the end result of this process is to get a vector representation of a word meaning. We've known how to do that by doing counts of words in context of other words for 20 or 30 years. It's a technique that distributional vectors are a technique that comes from the information retrieval world, and it's very, very widely used and very old. This is a different take on a similar thing, which doesn't actually use those distributional properties directly. And the way it works is the first time I came across this, I thought, what on earth, how would that possibly give you anything interesting? But it does. So what you do is get a large amount of data, and an advantage of this thing is that you can train on billions and billions of words of data effectively. You create training data by doing the following. You fix a length of vector, 50 is a good length. Decide on how long an n-gram you're going to use as your training examples, let's say 5, and we just pull out n-grams at random, and from each n-gram, and treat each of those as a positive example, and we create a negative example by just replacing one of the words by a randomly chosen different word. And we treat that as the negative example. So my made-up example here, actually the first thing is from a BBC. So photographer visits Syrian refugees in, and then my negative example is photographer visits Syrian refugees quark or bubblegum or something different. And then you make the objective function that you're trying to learn something that just simply gives the good example a better score than the bad example. And you can use standard neural network techniques for doing this. The trick is that you simultaneously regard the vectors for each of the words, you kludge them all together into a very big matrix and treat that as if it was a matrix of weights as in standard neural network things, and use the same back propagation algorithm to propagate changes into that matrix. So the result is that magically, over a long period of training, the vectors associated with each words acquire weights which somehow or other capture many of the semantic properties of those words. And the results are really quite interesting. So here's some examples. So once you've got vectors, of course, you can do clustering, because you can just do cosine distance measure between different vectors. So here's some examples from work by Colabert that I'm going to talk about in a moment. So if we look for the vectors that are nearest to the vector for France, we find things like Austria, Belgium, and Germany. Well, that's pretty good. It's not the only way of doing clustering, but it's nice that it shows us that we're capturing something. Synonyms or words that are semantically close to scratched, you've got there, nailed, smashed, punched, scraped, slashed. What's near to an Xbox, Amiga, PlayStation, and so on and so forth. So that's good. So it can do all the things that standard vector methods can do. But amazingly, you can also do some clever things by quite simple operations on vectors. So intuitively, if I take the vector for Paris and I subtract from that the vector for France, then add the vector for Italy, I get a vector, I get a vector which doesn't correspond to anything, but I ask, what's the nearest vector to it in that space? And the answer turns out to be Rome. And similarly, sushi, take away Japan, add Germany, get this thing that I can't pronounce properly. It's a kind of sausage. It doesn't always get it right, so it thinks that the kind of national dish of France is tapas and the national dish of the USA is pizza. I don't know, that may well be true. And in politics, so take Sarkozy away from France, and I guess many French people wish you would, but then add Berlusconi, you get Italy. So this is fascinating. So it actually captures some real analogical structure. So they seem to be capturing something quite meaningful. So that's pre-training, and what it's tried to do is to, on the basis of kind of, free-ranging over unstructured data, figure out in advance some regularities that will come in useful in the learning process. So Ronan Colobert was the first person to use these similar embeddings as a pre-training for a fairly straightforward, after that, general neural network model, which does many of the standard natural language processing tasks, part of speech tagging, noun phrase chunking, named entity recognition, sort of classifying into person, organization, location, and so on. And semantic role labeling is this thing, the agent of the verb, or the patient of the verb, or the instrument, and so on. And on the benchmarks that they chose to compare themselves against, which were other machine learning methods, you can see that there are some small but useful improvements on on 3 out of 4 of those tasks. So we creep up a tiny bit on part of speech tagging, a tiny bit on chunking, a bit on named entity, goes down a bit on semantic role labeling, which is actually a much more difficult task, and one which is in some sense much less local than the others. Okay. A number of groups have also tried to look at, including mine, have tried to show that using these pre-trained word embeddings will improve performance on other tasks. I should say, actually, in our group, we've had mixed results with this. In one setting, we found it did help. In another setting, we found we got just as good results with completely randomized vectors. So who knows what's going on there? But this is science. You have to sort of flail around until you figure out what's going on. But the one that I'll talk about here, because it's the simplest, is Richard Socker's parser, which is now the version of the Stanford parser that you get if you use the online Stanford parser or download the Stanford Natural Language Tools package. And the way in which it uses these pre-trained vectors is to associate a vector with each word, as we've already got, use a kind of standard probabilistic context-free grammar parser backbone to provide training data, and is actually part of the final system as well. And what we're trying to do is to, from the word vectors, figure out a way of also getting meaningful vectors for phrases, it's very similar to the compositional sentiment system I was describing yesterday. So we want to combine a verb vector with a noun vector to get a verb phrase vector, and so on and so forth. And the way that we do that is, again, very similar to what I was talking about yesterday, although not exactly the same. We given a binary phrase, we concatenate the vectors of the 2 daughter units to give you a long vector, and we learn a weight matrix that will take that. So if the word vectors are n long, the combined thing will be 2n, and we need to get a matrix that will multiply that vector to get us back something that's n long again. And we can learn that weight matrix again using standard neural network backpropagation methods. But what we do is learn a separate one of these corresponding to each syntactic combination. So we learn a separate one for combining subjects and verb phrases, another one for combining determiners and nouns, and so on, for every combination that you'd have in the grammar. And this works much better than just learning one big overall matrix. And at runtime, we can also, since we've got a probabilistic phrase structure grammar as a basis, we can stick the probabilities from that into the score. And the way that this is used at runtime is actually, it turns out to be too inefficient to do the parsing completely with this method. There are just too much computation. So a better way to do it is to use the simpler parser to give you, let's say, the 200 or 300 best candidates for a sentence, and then use this method to filter those down to find the best, and that gives you the right combination of speed and accuracy. And in fact, that combination gives you quite a considerable boost in accuracy from on the usual kind of test sets for sections of the Penn tree bank. Goes up from 80, just below 87% to just over 90%, which is quite a substantial reduction in error. So that all looks good, but I'm going to conclude with some words of caution. Deep learning is a really interesting technique, and it has lots of promise. It's intellectually fascinating, and actually seems to work quite well in practice. But it's not a magic bullet. I'm old enough to remember when expert systems were going to solve all the world's problems. And every 10 years or so, there's some new technology, Bayesian networks or graphical models and so on. And there's a great wave of enthusiasm, and then people realize that actually, it's only a bit better than what came before, but not a complete breakthrough. And I sort of worry about the way that deep learning is reported in the press. I mean, I've seen some just crazy, overblown claims for deep learning in the press. Very naive as well, and I wouldn't like this to be setting us up for another AI winter. We've had too many of them. So I'd point out that improvements from deep learning in natural language processing, I must say in vision and in speech, the improvements are much more substantial, and also in vision and image recognition, the notion that the different levels of a multi-layer network correspond to successive levels of abstraction is much more compelling. I mean, you can see the networks learning things from kind of very low-level input to much more successively more abstract levels of structure in a very impressive and interesting way. But the improvements in natural language processing, where there are improvements, have been generally quite tiny, and it's actually the case that many of the best performing systems are not based on deep learning. So, for example, the standard, the best performing parsers around at the moment are the ones from Berkeley and from Brown, from Charniak, and they're a notch or two, several notches more accurate than Stanford's. In fact, if you look at some of the tasks, traditional rule-based systems are currently the best. So actually, the best named entity recognition system tested on the same data that we've been talking about for English is an entirely rule-based system. And it gives you a couple of percentage points more accuracy. And similarly for co-reference resolution, finding the interpretations of pronouns and definite descriptions, the currently best performing system is one that's entirely rule-based. So I want to conclude with these words of caution that deep learning is very interesting and it's going to lead to some useful things, but you shouldn't throw the older methods out in favor of something that's as yet, not completely proved itself. I've got 42 seconds left, so I'll stop there, and if there are any questions, I'll be happy to try to answer them.
I can project.
Well, there are some microphones here.
Okay, so it's so that it gets captured. Professor Pullman, thanks for this little bit of a lesson as well as your conclusions. I strongly agree with your comment about the rule-based methods. Do you think that's widely shared in the current NLP and text analytics fields?
I don't think it is, but I think I think there are various different reasons for that. I mean, in a sense, we know how to do rule-based systems, so there aren't any interesting research questions there. We also know that to get a rule-based system to work well, you need a lot of skilled people working for quite a long time, whereas the advantage of machine learning methods is that that kind of process is de-skilled, typically, because in the best case, you can learn in an unsupervised method from unannotated data. At worst, you need annotated data, but annotating data typically requires a lot less skill than rule writing.